All right, let's talk about a phenomenon that you have absolutely experienced probably 1,000 times, whether you're just walking down the street or waiting for a train. We're talking about the Doppler effect.
You know the sound, right? An ambulance is racing towards you, and that siren has this super high, urgent pitch. Nee. But the second it goes past you, the pitch just drops. Yo! So why does that happen? Well, that is the Doppler effect right there in action. And we're going to break it all down.
So first up, let's tackle that weird siren sound. It's time to solve this everyday mystery once and for all.
So here it is, the official definition. The Doppler effect is the apparent change in a wave's frequency because of relative motion. Now, the key word there, the really important one, is apparent. The siren itself isn't actually changing its tune. What's changing is how you hear it, how you perceive it, all because it's on the move.
But, a definition is one thing. To really get it, you got to see the waves themselves. And that brings us right to our next section, waves in motion.
First, just picture something that's not moving, like a parked car just laying on the horn. The sound waves coming off of it are like ripples in a calm pond. They just spread out in these perfect, even circles in every direction. The space between each wave is always the same.
But what happens the very moment that car starts driving towards you, horn still blasting? Well, the whole picture changes.
This is where the magic happens. As the car moves forward, it's kind of chasing its own sound waves, right? It squishes them together in the front, shortening the distance between each wave. So for you, the person standing there, more waves are hitting your eardrum every single second. And your brain interprets that as a higher frequency, which we hear as a higher pitch.
And then, whoosh, it passes you and starts moving away. Now the exact opposite is happening. The car is racing away from the sound waves that are trailing behind it. This stretches those waves out, making the distance between them much bigger. So now fewer waves hit your ear per second, and you hear a lower frequency, a lower pitch. That's the drop.
Okay, so we've got a handle on what happens when the source of the sound is moving, but what if the sound is just sitting still and you're the one who's moving? Let's take a look at the rules of this shift.
This little table makes it super simple. Just notice, it doesn't matter if the source is coming at you or if you're going toward the source. The result is exactly the same. The frequency you perceive goes up. It's all about the relative motion between the two of you. That's all that matters.
And just to add one more little wrinkle, the stuff the wave is traveling through, the medium, also plays a part. For sound, that's usually air. So, if the wind is blowing from the siren towards you, it actually helps the sound waves along, pushing them and increasing the frequency even more. If the wind's blowing against them, well, you get the opposite effect.
Okay, so this whole thing explains sirens. Big deal, right? Wrong. Its importance goes way, way beyond that. Let's move on and see how this one simple concept literally changed how we see the world, from radar to redshift.
Seriously, this is not some obscure physics principle. It is the secret sauce behind how police catch speeders, how we forecast tornadoes, how doctors can literally look inside our arteries, and, maybe craziest of all, how we know for a fact our universe is getting bigger.
Let's start with one we all know, or maybe fear. A police radar gun shoots out radio waves. When those waves hit your moving car and bounce back, their frequency has changed. The gun just measures that tiny shift to calculate your exact speed. Pretty clever.
It's the exact same idea for predicting the weather. Meteorologists bounce radio waves off of things like raindrops in the air. By measuring that Doppler shift, they can tell not just where the rain is, but how fast and in what direction it's moving, which is absolutely crucial for forecasting dangerous storms.
And get this, it even works inside our own bodies. A Doppler ultrasound can send sound waves into an artery. Those waves bounce off your moving red blood cells, and the change in frequency tells doctors exactly how fast your blood is flowing, helping them spot things like blockages without ever making an incision.
But maybe the most profound, mind-bending application is in astronomy. When we look at the light from galaxies that are incredibly far away, we see that the light has been shifted towards the red end of the spectrum. That's the Doppler effect, but for light waves. And it's telling us that those galaxies are moving away from us. This red shift was the key piece of evidence that proved our universe is expanding.
Okay, for our final section, let's push this concept just a little bit further and go beyond the basics.
So, this is really important. The classic Doppler effect has its limits. It really only works when the object making the sound is moving slower than the sound waves themselves. Once an object, like a fighter jet, breaks the sound barrier, you don't get that neat little pitch shift, you get a sonic boom.
which is a whole different beast. And get this, we're not done with this effect, not by a long shot. Scientists are actually exploring some wild theoretical ideas, like an inverse Doppler effect. The idea is that in certain special, man-made materials, it might be possible for a wave source coming towards you to actually produce a lower frequency. It would completely flip what we expect on its head.
Which kind of brings us to our final thought here. From a simple siren all the way to the origins of the entire cosmos, the Doppler effect has been a key to unlocking the past. So the question I want to leave you with is this. As we get better and better at measuring these tiny shifts in waves, what is this fundamental principle going to reveal to us next about our universe's future?